Come on in, everyone. How's it going, Caden?
Hey, how's it going?
All right. Still got a few more. Well, just a couple more minutes. I only got about 5 people in here now, though, so that's not quite enough. Anybody have any questions before we get started? You're welcome to ask them. Another person came in. That's good. All right, got a couple more people who just came in, and we should go ahead and start, just to let you guys know. We are in chapter 4. I've already given you an intro to some extent on Newton's second law. Told you how we draw free body diagrams, and now now the yawning starts. Anyways, so now I want to show you how to make use of Newton's second law for some very specific problems. In it, we'll learn a little bit of physics in general. So basically, the fundamental principles of how tension in a rope distributes itself, that sort of thing, as well as tricks to solve systems of equations, so on and so forth. So I'm going to start off with a very specific diagram, and I'm going to solve it in a very specific way, and hopefully it'll be somewhat instructive. So let's turn on the sharing screen, namely so you'll stop looking at me yawn, because I can't stop yawning for some reason. Obviously need a sleep apnea machine or something. All right, this should be coming visible any minute now. All right, so I'm going to draw a level surface, and then I am going to draw a box that has a mass of 7.00 kilograms. That's attached to a rope that has a box of 20.0 kilograms. And that, of course, also has a rope, and that rope is attached to a box of 10.0 kilogram mass. And then there's another rope up here, but in this case, the force, which is horizontal, is going to be 100.0 newtons. And what I'm going to say is that the surface is frictionless. and rope / string. Another person came in. Is massless. So I have these masses here. They're sort of in a train, if you will. And I'm going to use this to show you how Newton's second law can be applied to a very specific object, or sometimes you can change it up and put it in terms of a totally different specific object. And actually, I'm not happy with my 7 kilogram box, so I'm redesigning it. Sorry about that. So let's do now. Whoop, I did not mean to do that either. I did not mean to do that either. That was not helpful at all. I need to go away. Okay. So I'm going to do a black box right here, and its mass is 7.00 kilograms. Now, what I'm going to put right here is a tension that I'm going to call T2, and what I'm going to put right here is a tension that I'm going to call T1. And what I want to know is, what is the acceleration of the entire train? What is tension T1? And what is tension T2? So that's the big question. Okay. Now, Newton's second law, like I said, applies to any object of mass m. So when you say the summation of forces acting on a system is equal to the mass of the system multiplied by the acceleration, when you decide on what the system is, then you got to use the appropriate mass. So in this case, it turns out there's a couple different things you can use as the system. And I'm going to try to show you the advantages of each. So first off, I'm going to treat the 7 kilogram mass as a system. So solution. Part 1, treat 7.00 kilogram mass as the system. Okay, so when I do that, I'm going to draw my coordinate system. So there's a coordinate system. There's my y-axis. I'm going to say this right here is my x-axis. This right here is my 7.00 kilograms. The force acting on this are, let's say, in the upwards direction is a green normal force, which I'll call N sub 7. And then in the downward direction, there is a 7 times 9.8. So 7 times 9.8 is equal to 68.6. So this is a 68.6 Newton mass there. And then I see basically my test, remember, to make sure I've done everything is I look at all the objects touching the system. So in this case, I had a floor touching the system. That resulted in a force N7. So that one's taken into account. I don't have any friction, so I don't have to worry about that. I do have, in addition to that, a rope on the right-hand side. That's in the positive direction. So I'm going to draw that here as T2. And that's one of the things we're ultimately wanting to know as well. And then finally, I have to consider the things that aren't touching it. And that can only be gravity. Gravity, electric force, magnetic force, strong nuclear force, weak nuclear force, which for us just means gravity. So I've definitely taken into account everything. And in this case, we're not dealing with friction, so I really don't even need the normal force, but I put it there for completeness so we'd actually see. So what I'm going to do now is I want to say the summation of the forces in the x direction is equal to mass times acceleration in the x direction. Now, what I'm going to do is I'm going to change that a sub x to just a, because if you look at this and you treat the rope or the string or whatever it is like we normally treat it in physics, which is it can't go slack and it's not going to stretch. Okay. Also, I'm treating it as if it has zero mass, but all three of those things combined tells me that if I pull the rightmost part where the 100 newtons is acting, if I move that 1 inch, then T1 is going to move 1 inch the same direction, and T2 is going to move 1 inch the same direction. So that means their motion is somewhat related. If I go further and say I'm going to move the string that I'm pulling with 100 newtons, I'm going to move that 1 inch in half a second to the right, then I see from that that T1 is going to move 1 inch in half a second to the right, and T2 is going to do the same thing. So that tells me the velocity of the rope in T2 and the velocity of the rope in T1 are exactly the same as the velocity of the rope that the 100 Newton tension's on. And finally, if I say in the first second, I move 1 inch in a half a second, and then I wait 1 second and move 2 inches in half a second, then that exact same thing will happen to T1 and that exact same thing will happen to T2. So I see that the acceleration is the same for all of them. So that's why I can just call that A. And all that hinged on was that the ropes are not going to get slack and the ropes are not going to stretch. So with that in mind, all I get is T2. That's the only force acting in the X direction. And that's got to equal 7.00 kilograms times A. I'm going to call that equation 1. Now I'm going to draw another free body diagram for the 20 kilogram mass. And I'm going to do that as follows. This is going to be my y-axis. This is going to be my x-axis. Notice how I made the positive x direction the same for both of these. That's not completely necessary, but it's crazy. It's crazy not to, and you end up having to do a lot of stuff if you don't. So we'll get to more on that later. All right, so in this case, I have a mass that has a mass of 20.0 kilograms. I have acting on it a normal force, which is acting in the positive y direction, but really doesn't matter too terribly much because we're not dealing with friction, and friction happens to be proportional to the normal force, which is the reason why we normally need it. We also have a weight. And of course, weight is equal to mg. And that, of course, is 20 kilograms times 9.8. I know 2 kilograms times 9.8 is 19.6. So this is going to be 196.0 newtons. And that's one extra sig fig, obviously. So I've got that one. And also I have pointing to the right is the tension T1. Whoa, no. Is the tension T1. And then, of course, the test, as always, is what's touching the 20 kilogram mass. Well, I see a rope that has a tension T1 touching it. I see a floor that's touching it. And then I see a rope that has a tension T2 touching it. So I haven't included the force due to T2. So I'm going to put that in there now. And notice it's going to act this way because if you're thinking about it from the block's perspective, you would say it's as if this rope T1 is pulling me to the right, but this rope on my left is fighting that. Therefore, I'm going to say that's pointing in the negative direction. So again, I'm going to take the summation of the forces in the x direction equals mass times acceleration in the x direction. And of course, I'm using the new knowledge that I have, which says that the acceleration's a constant for all of them. Okay. Now, in this case, I have T1 minus T2 is equal to 20.0 kilograms times A, and I'm going to call that equation 2. Okay. So now you've seen me use F equals ma for two different systems. The first system was a 7 kilogram mass, and now the second system is the 20 kilogram mass. Now I'm going to do for a third system, which is the 10 kilogram mass. So again, I'll draw my free body diagram. Okay. Again, this is my y-axis, this is my x-axis, and my mass in this case is 10.0 kilograms. I have acting on it a normal force, which again doesn't matter too terribly much to us, but that's going to be called N10. I have a weight acting downward, which is W equals 98.0 newtons. I have a force on the right that's 100 newtons. And then I have a force on the left, which according to the 10 kilogram mass feels like that rope back there is tying me down. So lo and behold, I've got a negative pointing T1 here. Okay. So again, I start off with my summation forces in the x direction equals mass times acceleration in the x direction. In this case, I get 100.0 newtons minus T1 is equal to 10.0 kilograms times A, and that's going to be equation 3. Okay. And it looks like I didn't write that very big, so I'm going to make that a little bigger. Okay. So there's 3 of our equations. Now, once and for all, I'm also going to consider the system to be all of the masses at once. And what you'll see is when I consider all the masses at once, clearly they're going to have a mass of 37 kilograms. But notice I won't have forces like T2 and T1 acting on it because T1 and T2 are internal forces that are holding the system together when I treat the system to be all of them. So that's part of what I wanted you to see. And the other part of what I wanted you to see is what you can't solve for as a result of choosing that system. So since I can't include T1 and T2 in there, I think you can see that that means I clearly will not be able to solve for T2 or T1. In this case, I have a 37.0 kilograms. 20 plus 10 is 30, plus 7 is 37. That's where that came from. I have a normal force, which I'm just going to call N, acting upward. Okay. I have a weight acting downward, which in this case, obviously, is 37 times 9.8. That's going to be huge. And that gives me 362.6. And that's the weight there. Now, what I see is I do have a force acting to the right, and that force is, in fact, 100.0 newtons. But there's no other forces, okay? Because again, we're treating the 7 kilogram, the 20 kilogram, and the 10 kilogram mass as if they're one big object. So forces like T2 and T1 are internal forces. They're not part of it. There's no friction on this, so I can't have that. So all I really have, I have to check and make sure, have I did everything that's touching all of them? Well, the only things that's touching all 3 of them is the floor. And of course, the force that the floor applies is the normal force. And of course, the tension in the right-hand side where someone's pulling it, that's the 100 Newton force. And then of course, that's all the things touching it. And then all I'm left is to check gravity, electric force, magnetic force, and the nuclear forces, which again, in this case is just the weight. So I've got the gravity down pat. I'm going to go ahead and write the summation of the forces in the x direction is equal to mass times acceleration in the x direction. In this case, I'm going to get 100.0 newtons is equal to 37.0 kilograms times A. And I think you can now see why I wanted to do that, because now I can get A and then plug it in one by one in those other equations and make everything nice and easy. So A is going to turn out to be 100.0 newtons divided by 37.0 kilograms. Now remember, a newton is a kilogram meter per second squared. So when I divide it by a kilogram, I'm just going to get a meter per second squared. When I divide 100 by 37, I get 2.703. And that's meters per second every second. So I now have the acceleration. That's the acceleration that the 10 kilogram mass will be going to the right with. Since the rope will not get slack or stretch, the 20 kilogram is going to be going to the right at the same acceleration, and the 7 kilogram will be going to the right at the same acceleration. So I got all that. I'm going to call this expression 3. So now I'm going to plug 3 into 1, 2, and 3. So when I plug it into 1, what I get is T2 is equal to 7.00 kilograms times 2.703 meters per second per second. And I'm going to say 7 times that acceleration gives me 18.92 newtons. And I've got one extra sig fig there, obviously. So that's 18.92. Notice that that tension happens to be exactly what's necessary to accelerate a 7 kilogram object at 2.703 meters per second, because clearly it came from multiplying 7 times 27 or 2.703. So that's a little bit of the physics that we're learning here, is that clearly the physics tells us that the individual tension in the rope is only responsible for the things to its left. Okay. So now I'm going to plug this in 2. And in this case, I'm going to get T1 minus, now I'm going to write in T2 here. That's 18.92 newtons. That's T1 minus T2 is equal to 20.0 kilograms times 2.703 meters per second per second. So in this case, what I got to do is take that 2.703 and multiply that by 20. And that gives me like 54.05. And then I add 18.92 to it. So and that gives me 72.97 newtons for that one. Notice in this case, you need 2.703 times 20, which is the 54.04 newtons, just to accelerate the 20 kilogram mass to 2.703. Notice that means the extra 18.92 is the tension required to accelerate the 7 kilograms. So you can see T1 is responsible for that and the other one. Okay. So now that you see that, you can see also that with equation 3, we can just use that as a check, and we'll say 3 as a check. what I'm going to do is say 100.0 newtons minus 72.97 newtons equals, with a question mark over it, 10.0 kilograms times 2.703 meters per second per second. Now, 10 minus 70, or excuse me, 100 minus 72.97 is going to give me 27.03. And then, of course, if I multiply 10 times 2.703, I think you can see what we get there is clearly 27.03. So this checks. So yes, we did get the right answer. We even confirmed it using all four of the equations. We only had all three of the equations. We only had two unknowns or three unknowns, so we only needed three equations, but we had access to 1, 2, 3, 4 of them. Obviously, I called equation three twice, so that was a boo-boo. Anybody have any questions on that? So this equation three, I'm going to change to equation four. Whoa. I'll put it in red so everybody will notice it. So that was equation four. And that should have been equation four right here as well. So let's do that. Okay, any questions on that? Any questions on anything else? All right, so that's a problem. Notice how if we actually use the total of all three masses together and treat it as one 37-kilogram object, I can easily get the acceleration. And in fact, in equation four, we saw that that was lickety-split easy, right? But it's completely impossible for me to figure out tension T1 and tension T2. Okay, we haven't really discussed tensions, by the way, so don't worry too much yet about it. I'm going to do another problem in a second, and that's going to be another tension, and we'll talk a little bit more about that. But notice also that if I did the individual tensions, or excuse me, did the free body diagram of the individual masses, then I had three systems, and that gave me, of course, three unknowns, T1, T2, and A. It's really not as bad as it sounds, but basically what you could do at that point is you could solve equation 2 for T1 and plug that into equation 3. And then you could use equation 1 and plug that in for T2 in the new version of equation 3. And you'd pretty much just have no unknowns except for A. That would allow you to solve for A, and hopefully you'd get the same 2.703. So you could have done all of that without that last diagram. That would have got it for you. But by not doing that, I would have escaped the opportunity of showing you how sometimes doing that can actually help you. When we go to the Atwood machine, which is when you have a mass on a pulley or a mass on each side of a pulley, you do not want to do ever do you want to do F equals ma for both of the masses at the same time. It's just too easy to make mistakes, so don't do that. Okay. So everybody write that down. Do not make one F equals ma for the whole system when doing Atwood's machine. All right, let's do another problem. And this one is more or less like your textbook. So I want to show you that. I'm going to first off take a pulley and put it down here. Okay, and then I'm going to take a cantilevered beam, also called cantilevered beam, like this. And that's going to be hanging over the edge of a building, say. And this is going to be my building. Got another person coming in. Okay. So what I'm going to do here is I am going to take this mass or this pulley and attach it to a really big mass. God dang it. I'm going to take this pulley and attach it to a really big mass, which for some reason this stupid thing did and ruined everything. Okay. So what I'm going to do is assume this is attached to a ginormous weight. Okay. Let's say this mass is 400.0 kilograms. Okay. So that's something we want to lift. I'm also going to put another pulley right here. Okay. And now I'm going to run my rope from this pulley down to that pulley. And then I'm going to run, actually, let me see if I can move this over here because that would be really helpful if I could. Not good enough. Okay. Now I'm going to run this rope from here back up to the beam, the cantilevered beam. And then I'm going to run this rope this way. And let's say we put a force on it of F. So what we want to figure out is what force is necessary to actually accelerate this upward at 0.70 meters per second every second. So I'm going to say A is equal to 0.700 meters per second per second. Okay. So what I want to know is what is the tension in the rope that's really required there. So I labeled it F, but you're going to see in a second that it's tension. Now, here's the weird part about dealing with tension. So I'm going to draw a free body diagram for that pulley at the bottom. So here's my free body diagram, which I'll label FBD. Okay. I'm going to draw my pulley the worst way I possibly can. Okay, that looks pretty good. Now, on the right-hand side, there's going to be a tension pulling up. And I'm going to call that F. Let's call that F sub T. We'll make that for both of them. And then, of course, since this pulley, which we're going to assume for right now, later we'll get into rotational motion and we won't have to assume that pulleys are massless. But if the pulley at the top there is massless, then when I pull with that tension FT, then the tension after the pulley will it be exactly the same. The reason being is think about the counter example where the mass of the pulley is not zero and maybe even the pulley has friction on it. If I'm then pulling down and to the right on that FT, then that tension that I'm applying has to not only lift all that stuff to the left of the pulley, in other words, the 400 kilograms and the pulley that's associated with it and all that junk, it also has to rotate that pulley. And to do that, of course, means the tension on the right-hand side of the pulley has to be larger than the tension on the left-hand side of the pulley. So for that reason, we can make the argument that the tension on the right and the tension on the left are the same. Okay. And we could do that same thing for the pulley at the bottom. And that's what I'm going to draw now. I'm going to say there's a tension pulling up here as well, and that has the same value, Ft. And then 400 times 9.8, I think it's 392.6, I think. 3,920. That's what it was. Okay. So what I have acting here is another force acting downward. That's 3,920 newtons, which equals weight, which equals mg. Okay, that's what we just used. Now, what I want you to look at here is one, I don't want you thinking that, oh man, I really should have been able to come up with this myself. I'm not, you can, it just might take a while. The important thing here is not whether or not you came up with this on your own, but rather now that you've seen me do it, you should be able to do it. And what I want you to notice is that the tension on the right and the tension on the left are the same. And that's always going to be the case if the pulley is massless and frictionless. Okay. If it's got friction or it's got mass, then one of those tensions has to be bigger than the other because one's got to rotate the pulley in addition to all the other stuff that the rope is doing. Okay. So now I can take the summation of the forces in the y direction is equal to mass times acceleration in the y direction. Again, that's the only acceleration we're dealing with, so I'm not even going to subscript it. I think what you can see is that we have two forces of Ft pointing up, so I'm going to write 2 Ft. And yes, this does say the sum of all the forces on the left, but because this W equals mg is in the downward direction, it has a negative component. So technically what I'm doing is adding a negative number, but I'm not going to waste my time drawing a plus and then a minus sign after it. So I am going to, in fact, just say minus 3,920 newtons. And that's equal to, of course, the mass, which is 400.0 kilograms times A. Okay. Any questions on that? Well, we do know the acceleration, so we can go ahead and say that Ft is going to be equal to 400.0 kilograms times 0.700 meters per second plus 3,920 newtons. And then I got to divide all that by 2 because the 2 was there before. So that gives me the tension force is going to equal 400 times 0.7. That gives me 280 plus 3,920. That gives me 4,200. So I'm going to say 4,200 newtons over 2, which ultimately gives me just 2,100 newtons for that one. Okay. Now, if you were just barely trying to lift this thing as opposed to actually accelerating it upward, what you would have done is set that equal to MA and you'd let A be 0. And then you're trying to find the force at which that's just barely equal to 0. And what that means is if I add, a single iota of force more than what I get, then that will go into actually accelerating the 400 kilograms upward. When you look at it that way, then you can see, oh, if I didn't have any acceleration at all, then basically I would be taking 3,920 and dividing that by 2. And that would give me 1,960, which is literally half of the weight that I wanted to lift. And that's the mechanical advantage of the pulley. The mechanical advantage of the pulley is a factor of 2, and that means it's a force multiplier. Like if I put in 100 newtons, then out pops 200 newtons. If I put in 1,000 newtons, out pops 2,000 newtons. So that's kind of helpful to know about, and that also ties us back to simple machines that we learned in grade school. Now, what we'll learn later is there's a concept called work, which is really the amount of energy put into the system. And you might suspect that conservation of energy would say you're not going to be able to just make energy. So if I'm making the argument that I got an extra, 1,960 newtons of force, then that's going to be lost somewhere. It's got to be, because otherwise it's like I'm getting something for nothing. Well, here's the deal. Can anybody tell me, if I'm up there at the top of that building and I'm applying the FT question mark at that top pulley, if I pull that rope a full 2 inches, how high is the 400 kilogram mass going to go? Can anybody tell me that? No one yet? Let's check my chat to see if anybody posted on the chat. There it is. I see nothing. Thank you. Yeah, Infinity did go ahead and put down her role, her first and last name for role. Please, everybody else, go ahead and do that while you're thinking about it. This is late enough in the class to do it. So what I'm saying is, if the rope at the top of the building is pulled 2 meters with a force of 1,960 newtons, then the 400.0 kilogram mass will, actually, let's do it. Which weighs 2 times 1,960 newtons, which equals 3,920. Okay, so pulled 2 meters with a force of 1,960 newtons, then the 400 kilogram mass will move 1.0 meters upward. So notice, yes, I got a force multiplier, but by doing a force multiplier, I ended up getting a distance divider. And that's the way things should be when you're doing mechanical advantage. You can use the mechanical advantage to increase your force, or you can use the mechanical advantage to increase the distance that you travel, that you move something. But the flip side of it is going to be the opposite. So if you're using the mechanical advantage of 2 to increase the force by a factor of 2, then you're going to decrease the distance by a factor of 2. Alternatively, if you're going to use the mechanical advantage of doubling the distance you move an object from 1 meter to 2 meters, say, then you're going to have to actually double the force that's applied. So if you need to lift a 400 Newton object, you're going to have to actually apply 800 Newtons to do it. Okay. Any questions on that? All right, so that's how that's solved. Notice also how the tensions look like they're canceling each other out. So when I did the free body diagram, I got a tension FT on the right that points up, and there's a FT on the left that points up as well. And in fact, if you pulled those down, slid them along the pulley, you'd see the FT pulls to the right and the FT on the left pulls to the left. And since they're both magnitude FT, you'd see they cancel each other out. That's the nature of what it's supposed to look like. After you draw the free body diagram, your tension should look like they're canceling each other out. Notice that's also what they did here. Notice T2 in the middle diagram is pointing to the left, and T2 in the leftmost diagram is pointing to the right. So you can see that they are actually acting like they're canceling each other out. Anybody have any questions on that? All right. Well, there's another type of problem that we need to be familiar with. And this one I sort of call my fuzzy dice problem. So let's move on to this one. So I did a little bit of extra stuff with it in lecture today, but I don't think they were very excited about me doing it. So I'm going to choose not to do that this time. But let's take a rear view mirror of a vehicle. And let's say that's the rear view mirror. That's the actual mirror itself. And this is the actual mirror holder doohickey, if you will. So that slab that I'm showing you there is the side view of the actual mirror. And what I'm going to imagine is that we hang a little rope right here, and that rope is going to hang vertically downward. And then on the end of that rope is going to be a symmetric mass. And I'm being symmetric in this sense because I want it to be like a plumb bob. Actually, this thing is aggravating me already. It won't let me move it. Okay. Why won't it let me move it? All it's let me do is draw it up and down. Okay. I'm just going to pretend like that's centered up. But the main thing is if I put something like something shaped like this, notice the weight's not evenly distributed. So if I if I hanged this from a rope, there's a good chance that the rope would not hang vertically downward because this thing's odd shape is forcing it to hang at some angle so that the center of mass of this would be directly below the secure position of the rope. That's what's going to happen. So if you don't put something symmetric hanging from that rope, then this thing's not going to hang straight down. And that's what I'm trying to avoid. So what I am going to do now is I'm going to show that this is actually going to say the windshield like this. And what we're going to imagine is I'm going to sit in this car and take off. Let's say the object down here has a mass M. I'm not telling that to you. I'm going on the assumption that this M is ultimately going to cancel out, so I won't need it. Okay. But can anybody tell me what's going to happen with this mass if I hit the accelerator and start to accelerate to the right? What's that mass going to do? Do you see that if I hit the accelerator and the mirror and the string and the mass take off to the right, that's going to cause the mass on the end of the string to swing to the left because there's no reason for M to be accelerated forward until the tension in the rope tells it that it has to be. Okay. So what I'm going to do is try to figure out what is the angle theta for a given acceleration. So my question is, at what angle theta will the mass hang when the car accelerates at A. So that's the question, okay? So that's our diagram. What I'm going to do now is a free body diagram again. So there's my free body diagram. This is going to be my x-axis. This is going to be my y-axis. And I'm going to put the mass right here at the center and call that mass M. Now, acting on that mass M should be a weight acting downward, and that's going to be W is equal to mg. Now, what we're imagining is I'm going to hit the accelerator of this car and maybe like completely floor it in hopes of getting a uniform acceleration, at least for a couple seconds, or at least for a couple tenths or hundredths of a second. And then while I'm experiencing that constant acceleration, the string that the mass is hanging from is going to swing towards the back of the car. And as long as my acceleration isn't changing, that string will reach an equilibrium angle theta that differs from the vertical by an amount theta. And I will try to take a snapshot of that, say with a phone, and figure out what that angle is, and then use that to determine my acceleration. So when that actually happens, the string is no longer going to be vertical, but rather the string is going to be at an angle like this, and that angle is theta. Now notice that green line is vertical, just like the y-axis is vertical. There's a neat thing in geometry that we expect you to know as coming into calculus-based physics. So I've told you this before, but basically in physics, we assume that you've learned everything you were supposed to have learned from kindergarten up through all of your calculus course that you're supposed to have completed by now. So everything you've ever learned in grade school, middle school, as well as everything you've learned in college algebra, pre-calc, trig, all that good stuff. So one of the things we do learn is that if you have, for instance, two railroad tracks, obviously railroad tracks are supposed to be parallel, or the actual train will roll off of them, and that's not what you want. So when you have two tracks that are parallel, like the y-axis pointing vertically and that green line pointing vertically, now if you lay a bar across those two tracks, then something neat happens. And what it is alternate interior angles become equal. So notice the two thetas I've drawn there. The theta on the left is above the dashed green line. The theta on the right is below the dashed green line. And both of the thetas are between the quote unquote railroad tracks. That's what I mean by alternate interior. So as long as the railroad track part is parallel, then alternate interior angles are supposed to be equal or congruent. Corresponding angles are also congruent in that case. And of course, vertical angles are always equal. So there's a lot of different things in there, but the main thing is we needed that. So what you see now is a free body diagram that has a weight mg putting down, but we also have something else touching the string, touching the mass, and that's the string. And that string, of course, points right along that green line. Okay, and that makes a tension T. So what I'm going to do now is I'm going to realize that that tension, at least in the x direction, oops, that tension in the x direction is going to be positive, and the component of that tension in the y direction is going to be positive as well. And notice from where that theta is, you'd also reach the conclusion that, let's do it in this color, this too is also theta. So this guy becomes T cosine theta, and that's what we call T sub y. And this one becomes T sine theta, and that's what we call T sub x. Does everybody follow that now? So I had to break the tension, which isn't parallel to an x-axis or a y-axis. So I had to break it up into components that were parallel to the x-axis and parallel to the y-axis. Now I can use the summation of forces in the x direction and the summation of forces in the y direction. Summation of forces in the x direction is equal to mass times acceleration in the x direction, but that's the only acceleration, so I'm not going to subscript it. I also have the summation of the forces. Excuse me, that was supposed to be x. I don't know why I wrote that. The summation of forces in the y direction is equal to mass times acceleration in the y direction. Now, remember, I made some a bit of a fuss about trying to hit the accelerator hard enough that it's a uniform acceleration and holding it long enough that I can get a snapshot of it. Because what I want is when I take off, I want this string to be hanging vertically. And when I hit the accelerator, I want it to swing fairly smoothly backwards and then rest at that angle theta while I'm accelerating at a constant rate. Of course, the car can't always accelerate at the same rate for any period of time, or else it could go infinitely fast. So what happens is over time the acceleration gets less and less, and then the ball's going to start to swing and stuff like that. I'm trying to avoid all that and just get that equilibrium position where the ball goes up like this and then it rests there for a couple hundredths of a second or a couple tenths of a second. And in that case, I think you can understand that the acceleration in the y direction would in fact be zero. And that's critical, okay, for us to understand this. So now when I take the summation of forces in the x direction, the only force I have really is T sine theta, and that's got to equal m times the acceleration that the car has. I'm going to call that equation 1. And then I'm now going to do the summation of forces in the y direction. And in this case, I've got T cosine theta minus mg is equal to 0. That's not the prettiest way, so I'm going to solve this for T cosine theta and put the mg on the other side, and I'm going to call that equation 2. Okay. Now I have ostensibly two unknowns, the tension and the angle theta that I don't know. And I've got two equations, so I can do all that. What we're doing is we're pretending we either know theta and want to know A, or we want to know theta and we know A. Now I'm going to teach you a way to deal with this type of system of equations that your math teacher probably didn't teach you. And there's good reasons for math teachers not teaching you it, okay? But I'm going to show you a way that in the physics world, we do this quite often and give you the reasons that we do it. So it looks to me like what I should do in this scenario is divide equation 1 by equation 2. And when I say like that, when I say, hey, we're going to divide an equation, what I mean is I'm going to divide the left-hand side of one equation by the left-hand side of the other equation. So in this case, I'm going to have T sine theta over T cosine theta. Now I'm going to set all that equal to the right-hand side equal to the right-hand side. The right-hand side of 1 was m times A. The right-hand side of 2 was m times g. And you can see that the m's cancel out and the t's cancel out. And anybody know what sine theta divided by cosine theta is?
tangent.
Yep. So we're going to say tangent theta is equal to A over G. Now that's technically correct enough. If I wanted to solve for theta, then I'd say theta equals the inverse tangent of A over G. Or if I wanted to solve for A, I'd say A is equal to G tangent theta. Both of those are acceptable. Notice that the M's canceled out, the tensions canceled out, so I didn't really need them. Anybody have any questions on that? Now, you can actually use something like this. If you actually hang a plumb bob, that'll automatically have the right symmetry. But if you hung a plumb bob from a mirror and you had another person in your vehicle, you do not want to be dangerously driving and trying to take a snapshot or a photograph of something hanging from your rearview mirror while you're accelerating this. A lot of bad things can happen there. But if you had a second person with you, they could possibly take that photograph and then you could actually use it to measure what your acceleration of your car is. So does anybody have any questions on this one? All right. So the next thing I'm going to do is the Atwood machine that I told you guys about. So let's do an Atwood machine. Now, this result that we'll get is neat because it's an Atwood machine in the simplest scenario, but we'll make much more complicated Atwood machines. And because of the way nature works, what you'll find is the answer for Atwood machine in those more complicated cases actually reduces to the Atwood machine in this simpler case, as long as you make the right simplification. So for instance, if you had one side on an incline as opposed to just hanging vertically, then you might let the angle theta go to 90 degrees, and that should give you back the hanging vertically version of the Atwood machine. So I'm going to do this one symbolically because, as I told you, when you solve an equation, a problem symbolically, you've solved an infinity of problems. Whereas if you solve it with numbers, you've solved it exactly one problem. Okay. So let me draw my Atwood machine, which starts off with a pulley. So there's my pulley. I am going to say that there is a rope hanging down from the right side of that pulley, and that the mass on that side is ginormous. And I'm going to say that mass is capital M. Woo. Okay. Now I'm going to draw another string coming from the other side. It's actually all one continuous string, by the way. I'm just not choosing to draw over this top of the pulley to show all that. So it's one continuous string going over the pulley. I'm going to draw a much smaller box on this side and say its mass is little m. The implication being that clearly the big M evidently weighs a lot more than the little m, and therefore we expect the big M is going to go down while the little m goes up. Does that make sense to everyone? I'm going to say that the pulley is massless. So the pulley is massless and frictionless. Okay. And now what I'm going to do is, given the way I drew this, it looks pretty obvious to me that the big M is going to accelerate downward. I think that's the way I was drawing it and everything. So what I'm going to do is choose everything consistent with the big M going down on the right. I'm going to call that the positive direction. You don't necessarily have to do all this that I'm doing here, but if you don't, life can be a pain. So that's why I'm telling you. Okay, so I'm going to draw a free body diagram for the big M. So let's say FBD for big M. And I'm going to start off by drawing my coordinate axis, which in this case is just one dimensional because there's really no sense in having something going left and right in this scenario. So I'm going to say down is the positive direction, like that. I'm going to say, here's my mass, big M, and I'm going to say the force on this side is, of course, big M G. And if you were to ask, let's say, someone riding in that box of mass big M, they would say, well, thank goodness that rope was up there because otherwise I would have fell into the ground at 9.8 meters per second every second and possibly died. So that tells us that the tension is actually acting on the big mass and pulling upward. So what I'm going to do with that one is I am going to draw it in the, well, actually, I'll just do them both in the black, even though I was going to use a different color to represent positive and negative, but this is okay. I'm calling downward the positive, and I'm calling the tension is pointing in the negative direction, okay? So now I'm going to say the summation forces in the y direction equals mass times acceleration in the y direction, which again, I'm just going to call A, because if I pull the left mass down 1 inch in 1 second, the right mass will go up 1 inch in 1 second. So that tells you its velocity is the same. If I pull for the first second 1 inch, and then in the second second, I pull 2 inches, then the little mass will be lifted 1 inch in the first second and 2 inches in the second second. Therefore, the accelerations will be the same again. Okay. So what I get for this is big M G minus T is equal to big M A, and that's going to be equation 1. Does that make sense to everybody for my free body diagram and F equals ma equation? Anybody have any questions? Okay. Now I'm drawing a free body diagram for the mass little m. Okay. Notice this side I've got up being positive. So again, what I'm trying to do is say whatever the right-hand side does that is in the positive direction, anything that's consistent with that on the left-hand side needs to be positive as well. You don't have to do this, but otherwise you're going to have to make up another equation like A on the right is equal to negative A on the left or something stupid like that. And it's just not worthwhile. Okay. So you definitely want to try to align these like I'm doing here. I'm going to take my mass, little m, and put it right here. And then I'm going to say acting in the upward direction, in this case would be the tension. So there's the tension. Notice I didn't subscript the 2 tensions because the pulley is supposed to be massless and frictionless. If the pulley had mass, then the tension on the right would be required to not only lift the little m up and accelerate it at the same rate as big M, but it would also have to rotate the pulley and fight any friction the pulley had, and you'd end up getting T on the right being bigger than T on the left. But that's not what we had here. Now, the force that I have in the negative direction in this case is M, lowercase m times G. So now I can say the summation of the forces in the y direction is equal to mass times acceleration in the y direction. In this case, I get T minus little mg is equal to little ma, and that's going to be equation 2. So what we're pretending we know here is big M, little m, and G. The A and the T we don't know. So hopefully you remember from high school algebra or pre-calculus or whatever, one of the methods you use to solve equations was sometimes you'd take one equation and multiply it by a number, and then take another equation and multiply that by a different number, and then you'd add those two equations. And the reason why you multiplied is like you might have a 2x in the first equation and you have a 3x in the second equation. So if you multiply the first equation by -3, you get -6x. And if you multiply the second equation by +2, you get +6x. And then when you add the 6x and the -6x, they would cancel out. That was the way we did it. Notice here we have two equations that we could do that with, but one of the unknowns already has the additive inverse coefficient. In other words, one is the negative of the other. So you can see that if I add equations 1 and 2, the t's are going to cancel out. So let's say add 1 and 2. And what we're going to get is, and I'll write it all out, even though I normally don't take this many steps. I'm going to say big MG minus T plus T minus little mg. That's the left-hand side added to the left-hand side. Now the right-hand side, notice the right-hand side of 1 has a big M and a. The right-hand side of number 2 has a little m and a. So I'm going to go ahead and factor out that common a and write this as, well, I'm going to first erase it because this thing clearly wants me to erase everything. So I'm going to write m plus little m times a for the right-hand side. Notice the minus t and the plus t cancel out. That was the whole point. Now you can also see that there's a common factor of g. So when I go to actually save for a, I'm going to get a is equal to big M minus little m over big M plus little m. And then the g is technically, get this straight, guys. This is something that a lot of students sort of lose track of after years of math and going through calculus. But when I write that g to the side of that fraction, that g is being multiplied by the numerator. Okay, it's not being multiplied by the denominator, and it's definitely not doing both. It's multiplied by the numerator. It's the same thing as writing g over 1. And also, let me teach you something important about this. This way that I solved it, it has m minus m, which obviously both of those terms have the same units because you can't subtract or add things unless they have the same units, and they're both masses. So you expect it to be kilograms minus kilograms. But you notice the denominator has kilograms plus kilograms. So the whole fraction inside that parenthesis is kilograms over kilograms, which means no units. So that's a tried and true favorite way to save equations symbolically, where you have the thing that you're solving for, in this case, A, is an acceleration. So it'd be really nice to look at it instantly and know its units are acceleration. So by me putting that g out there, I know g has the units of acceleration. And then by me putting that fraction next to it, I know that that fraction has no units. So this is actually sort of one of the best ways you can write it. Now I'm going to call that equation 3. So I'm going to say now plug 3 into, I'm going to choose 2 just because the t is already positive there. So I'm going to say t minus mg is equal to ma, which gives me t is equal to mg plus ma, which you can see is basically m times g plus a. So now I can start solving for that. I'm going to say t is equal to m. Now g is just g, but I'm going to leave a space, and you'll see why in a second. But a, we know, is m minus m over m plus m. and then all that times g. So now I think you can look at this and see why I left that gap. I want to get a common denominator, and the least common denominator between 1 and m minus m over m plus m is m plus m over m plus m. Okay. Now, do keep, in this case, it doesn't matter too terribly much, but if there was a minus, a subtraction in the middle of that square bracket right next to that G and next to that parenthesis, if that was a minus, the thing I'm getting ready to tell you would come in extremely important. It's not a minus, so it doesn't matter too much, but I want to remind you that fraction bars are the same thing as parentheses. So you still have to distribute. For instance, if I'm multiplying that plus, that has to be distributed across the numerator. In this case, like I said, since it's a plus, it didn't matter. But ultimately, what I get is t. Well, I'll go ahead and go from here. I was going to go ahead and write it in red, but what I can do is I can see that there's a common factor of lowercase m, lowercase g. And then what I'm going to do is say the numerator of the first one is m plus little m. And then I have to do plus, and here's where I'm distributing it to the numerator of the second one. Again, it doesn't matter because it's a plus 1 that I'm distributing, so it doesn't matter. But I'm doing plus 1 times big M, and then I'm doing plus 1 times negative m. So that gives me a negative lowercase m. And then all this, of course, is still going to be over m, big M over little m, like that. And I think you can see that the little m is going to cancel out with the big M. And ultimately, what I'm going to do is I'm going to say t is equal to 2m over m plus m times mg. Notice how, again, I took time to write it as a dimensionless quantity multiplied by a dimension-full quantity, okay? Now, this m minus m over m plus m and this 2m over m plus m, that's actually going to appear again later in a totally different type of problem. So it comes in handy to know it. And you'll see that it also will pop up a lot in other inclined plane problems. Anybody have any questions on this one? All right, one more I want to show you, and this is an inclined plane Atwood machine. Okay. So let's imagine an Atwood machine, but one side of it is on an incline like this. Okay. And let's say this angle right here is 36.87 degrees. And let's go further and say that this mass right here is 10.0 kilograms. And let's say it has a string running parallel to the incline and then going over a pulley and then hanging on this side is supposed to be a really big mass of 40.0 kilograms. Again, this is going to be a frictionless scenario though. I actually need to make both of these boxes a little bigger. Okay. And let's do this one too. So what I'm going to do here is say this is 40.0 kilograms. Okay. Now, it turns out when you're dealing with inclined planes that sometimes it's better to actually tilt your coordinate system uh, to be parallel to the inclined plane. And that's what I'm going to do now. So I'm going to draw a coordinate system that has x pointing up the incline and y will be this way. And right here is going to be a mass of 10.0 kilograms. Okay. Now, obviously, that has a force. Notice I drew it a green axis because it's not aligning with either the x-axis or the y-axis. But in fact, this is going to be 98.0 newtons acting this way. Now, I do have a tension going up the incline, so I'm going to draw that black and call that T. And I also have a normal force, which again doesn't matter here because it turns out that the normal force only matters when we're trying to calculate the friction force, and we're ignoring friction. So what I can also say is that the component of the weight in the x-axis is that little guy down there, and the component of the weight in the y-axis is this little guy. Now, here's a little bit of the quote-unquote tricky part. If this is theta, which we know is 36.87, then you can sort of see that this makes a right triangle right here. So that means this angle would be 90 minus theta. But then you can see that, wait a second, this angle and this angle is also 90. So this little guy right here must be 90 minus 90 minus theta, which I think you can see is theta again. So this guy is going to become 98.0 newtons times cosine 36.87. I'm going to go ahead and punch that number in. 98 times cosine 36.87. That gives me 78.4. Oops. Equals 78.40 newtons. And then this guy is going to be 98.0 newtons times the sine of 36.87. And that's going to give me 98 times sine 36.87, which gives me 58.80 newtons. Again, extra sig figs are all over the place. Okay. Now, I also have a free body diagram. Notice I drew going up the incline as the positive direction. So when I do the free body diagram for the hanging mass, this is the positive, let's call it positive x direction, just to be consistent with what we did before. And in this case, the mass is 40.0 kilograms. And that's going to give me a force of 392 newtons here. And of course, there's also going to be a tension slowing it down, and that's T there. So if I take the summation of the forces in the x direction equals mass times acceleration in the x direction, and again, I'm going to make the same argument that there's only one acceleration to deal with, then in this case, I just get T minus 58.80 newtons is equal to 10.0 kilograms times A. And that's going to be equation 1. And then I can take the summation of the forces in the x direction equals mass times acceleration in the x direction, again, A. But this time it's going to be for diagram number 2 down there. In this case, I'm going to get 392 newtons minus T is equal to 40.0 kilograms times A. and that's going to be equation 2. Now I add 1 and 2, and you see that you're going to have basically 392 minus 58.8. That's going to give me 333.2 is equal to 50.0 kilograms times A, because when you add 40 kilograms and 10 kilograms, you get 50. So I can automatically say A is going to be 33.2 divided by 50. That gives me 6.64, actually 6.664 meters per second every second. That's the acceleration. And now all I have to do is say T minus 58.80 newtons is equal to 10.0 kilograms times 6.664 meters per second. So I'm going to multiply this by 10, and now I'm going to add to it 58.8. And I see that the tension T is equal to 125.4 newtons. Okay. So that's how you would actually work that problem. I would highly recommend you going back and calling this big M and little m and seeing if you can solve it graphically or symbolically again. But you guys are done. I ran over by 3 minutes. Oop, it just changed to 4 minutes. I ran over by 4 minutes. Of course, you're always welcome to leave if you're in a rush when I do that. So don't feel bad. Make sure everybody puts your name down in the chat, first and last name, so I can use it for roll. Other than that, you're free to go, and I'll wait for the last person to leave in case anybody has any questions. Is that you, Shakayla?
Oh, yes.
Yeah, I thought I saw you come in quite a bit earlier. And I actually did see your text message that you sent me. I figured I'd answer it tonight after my class. That's why I hadn't replied yet. But what's going on? How can I help you?
Okay, yes. I didn't know that the moon observations were due on Saturday, and normally they're doing Sundays, right?
Yeah, that's a mistake by I must have just put the wrong date in, but let me check it real quick and see if I can fix it for you. But yeah, so don't worry about that. I'll take care of that. In fact, I'll go ahead and make it like due Wednesday. That way it'll give you time to put it in.
Okay, yes, that was my only question because I was trying to do it last night, and I was like, oh my goodness, it was due yesterday. Like it was due on
Yeah,
Saturday.
that's a mistake. I didn't even know I did that. I'm glad you told me. But yeah, I'll try to. I'm opening it right now. It takes a little while for me to do it, so I won't be able to do it until probably after I get offline with you. But
Oh,
anyway, is that all you
okay,
had
and
for me, or you have something else I can help you with?
what about test two? Was that available yet, or it's not out yet?
Was it all test two? I thought I did put that out already. Let me check.
I didn't see it on my options. I know you released the practice.
Uh, this is taking forever for me to log in. I apologize. So
No,
much
it's okay.
stuff. Looks like it's opening back up now. Yeah, I meant to make those both available. I don't know why it's not, but let me check and see. I'm gonna go ahead and kill this. Actually, it's just me, you and I. I'm gonna go ahead and kill the